Seems the organizers have worked with the weather, so to make it more pleasant to be in the room inside. Outside is not as nice as it used to be, which is good. So before we start today, I want to just recap one thing that we didn't fully discuss yesterday, and that was the scaling, right? And to remember, we had this kind of speed-up curves that when you increase the number of processors, you should actually get better performance, which is what we call scaling. Now, there is actually two forms of scaling. There is strong scaling and weak scaling. Somebody heard about those concepts yet? So strong scaling is the scaling that you get if you have a fixed problem and you just increase the number of processing elements, the number of resources. So what you typically get when you do strong scaling, or what you want to get, right? You say this is execution time and this is the number of processors. Ideally, you would like to get a curve like that, right? In reality, as we learned yesterday, it's probably more like this somewhere, yeah? There's another form of scaling which is called weak scaling. And in weak scaling, we actually not only increase the number of processing elements, but we also increase the problem size. So if we double the number of resources, we also double the problem size. And the perfect curve then, of course, is like that. You want to stay constant, right? You double the number of resources, you get twice as much work done in the same amount of time. What do you think is easier to achieve? Weak scaling is typically easier. So if you have a problem where you can exploit weak scaling, then you are reasonably lucky because that's typically easier, right? It's still difficult. As we've seen, for instance, the example of the climate folks, they do weak scaling, right? They increase the grid points, right? They go from 10 kilometers grid to a 1 kilometer grid, right? So they're increasing the problem size, but it's still difficult to get the performance. Strong scaling is very hard because if you go to a large amount of resources, you tend not to have a lot of work left on each processor. And then you're getting into troubles. Molecular dynamics is one of those examples, right? It's only, you cannot build artificially large molecules. Doesn't make sense. Okay, that's just something to keep in mind. Today, we want to look a little bit on how we actually program HPC systems and also look a little bit what technological trends will be. So we said yesterday, in very simple terms, high-performance computing is that we take a problem and then split it up in subparts so that you can execute those subparts on the different resources that you have. Sounds very easy. The question is, how do I go about splitting up my problem into subparts? And there is two main techniques that you can use. The first technique is called task parallelism. The idea is that you decompose your problem into individual tasks, individual functions that then you can execute independently on the different resources that you have, right? So you take the whole problem instruction set and then you divide it into different tasks and you map those tasks to different processes. So a task is similar to a function, yeah? And that's why we also call this functional decomposition. So this is typically something where it's very coarse-grained, so you have relatively large tasks. Like when you do climate modeling, right, you have a model for the atmosphere, a model for the ocean, and so forth. And you can compute them independently, and then every now and then they exchange data, and you move on. Similar for ecosystem modeling, or you have signal filtering where you run a sequence of different filters over a signal, right? So it's a quite intuitive way of doing parallelism. Yeah? Once you have your tasks, then basically you could do that you put your tasks into a task graph, right, which denotes the dependencies. And say, okay, like task 5 can only be done once task 3 and task 2 is done, because otherwise it doesn't make sense. You can put some weight on the nodes, like the time it takes to execute a certain task, right? And then you can try to schedule this graph on the resources you have, right? And of course, the one thing is that you would like to have it in the best possible time, which of course is limited by the critical path that you have going through your graph, right? You can't be faster than the critical path. But then you would also like to reuse the resources efficiently, right? And if you come with a schedule like this, you see there is a lot of idle time in between here, right? So effectively, it's only 27% for most of the resources that are being used. So you could actually get much better resource utilization if you use fewer resources in this specific example. So that's what you do when you deal with task graphs, and of course there is lots of tools out there that help you with that, right? That go into the task decomposition, that build the task graph, because an optimal graph decomposition is actually an NP hard problem, right? So there's tools out there that take different resource requirements into account and help you with all that schedule. So this is a very natural approach. This is something that we are used to. We're used in that thinking. The problem we have is that in practice, the scalability of this is limited. If you remember, the largest machine we have today has 10 million cores. How can you extract 10 million independent tasks, independent functions in the problem, right? That's not very easy. So if we take as an example, you want to prepare a banquet, right? And basically you could say, okay, we exploit parallelism, and one chef prepares the appetizers, one chef prepares the salads, one the main course, one the dessert, right? So you only have a parallelism degree of 4. That's not a lot. How could we improve this? How could we get more parallelism in this? What is a typical caterer doing? You can have 10 people cutting the tomatoes, right? So you could actually exploit what we call data parallelism in here. The data is the tomato, right? So you're not cutting the tomato is the task, yeah? And you only have this one task. But then you have hundreds of tomatoes, and then you can actually distribute the data to the different resources, to different chefs. So this is what we call data parallelism, and it's the inverse of task parallelism. So here we're not looking at the instruction set, but we look at the data set, right? And we distribute the data set to the individual tasks. So this is then because we talk about the data domain, it's also called the domain decomposition. So we already discussed this. You could have, well, you need, say, n meals, and then you can have p chefs, and each chef prepares n over p meals, right? And as we discussed, you can combine it with task parallelism, right? You can have, on the outer level, you have tasks, and the inner level, you have data parallelism. The problem that arises, of course, is how do you distribute your data, right? Because then we again have this problem. With task parallelism, it's relatively easy, right? You know your tasks, and you have a task graph, yeah, where you build the dependencies. For distributing the data, you basically have a distribution function. There's some arbitrary function, right, that for each data index n tells you on which processor it is. Of course, there's also the inverse of the function. For each processor, you know which data indexes you have. You must know what you have. And this can be any arbitrary function, but of course, the more complicated you make this function, the more difficult it is, because you need to always compute. Is my data local? If not, where is it? From where do I get it? And so forth. Yeah? So that's why typical strategies include what we call a block or a cyclic distribution. In a block distribution, we basically take the data we have and we distribute it in equal-sized chunks. Right? So it's a very simple thing. A cyclic distribution, we just go round robin over our resources, right? One data item, each processor. And then you can replicate over dimensions, right? So here you replicate over the columns, here you replicate over the rows. This is two-dimensional, and so forth, right? All kinds of different distributions that you can have. So what you need to think when you say, okay, how am I going to distribute my data? You need to think, what is your access patterns? Right? If you're going to iterate over columns, then this distribution is good, right? Because you can iterate over the columns without needing data from somebody else. If you use this distribution and you iterate over columns, then you jump over the different processors all the time, right? If you iterate over rows, this is good. The second thing you need to think about is load balancing. The overall idea is that all resources get equal amount of work to do, right? So that you're not having anybody trailing, yeah? Because if you have, say you distribute your data over the processors and all processors finish in 5 seconds, but one processor finishes in 10 seconds, then the whole execution time is 10 seconds, right? And you waste a lot of resources because the others have nothing to do but waiting for the trailing processor, right? So one fundamental idea in parallel computing is load balancing. You need to make sure that everybody has this, roughly the same amount of work. That's why you get the most efficient and you avoid waiting time. And this is what you do also with the distribution, right? So this is a perfectly load balanced distribution here, of course, as well. But if you're not having a full matrix, if you have, say, only looking at the triangular matrix, yeah, then this is very bad, yeah, because you're not using this resource at all and only half of those resources. If you do this row-wise distribution, then it's actually even getting worse, right? Because this is having, I don't know, what is it, 10%, right, of the work that this guy has to do. So this is when block distribution actually is not very good. But if you have, say, a cyclic distribution, you automatically get a relatively good load balancing, right? That helps you with this. So these are some considerations that you have when you distribute your data. Now, how do you exploit parallelism when doing this? Typically, you do this via loops, right? The loop is basically where most of the work of the program is being done. So, again, basically getting back, what you typically do is you have a loop that goes over your whole data set. You say processor 0 is iterating over this data set, processor 1 over this, processor 2 here, processor 3 here, right? So you distribute your loop iterations to the resources that you have. What you need to take care of is dependencies, right? What do you need if there is dependencies that are carried by the loop? One loop iteration depends on the results of the previous loop iterations, right? You need to take care of that. and you can have dependencies inside the loop body. And then you also need to distribute your data, basically analyzing the access patterns as we've discussed before. So dependencies is a big, big problem in parallel computing because we cannot break dependencies, right? We need synchronization to make sure that dependencies are being covered. But if we have synchronization, of course, we lose parallelism. So that's not good. So if we have dependencies in the loop body, we actually don't care. Yeah? Because we distribute or we iterate whole loop bodies in parallel. So whatever happens inside the loop body is fine. You still need to look at those dependencies to think about vectorization, instruction level parallelism, and those kind of things. But from a parallel computing point of view, it's okay. What is problematic is when you have loop-dependent dependencies, right? If iteration x depends on the result of iteration x minus 1, it's a very common example. That prevents you to do parallelism. Special case here is that typically this is sometimes you have nested loops. Very often in scientific problems you have a huge outer loop, which is your time loop. And that carries the dependency, right, as you iterate over time. But then you have inner loops that iterate over the matrix, and that typically can be parallelized. So basically you try to move your dependencies to the outer loops, then you can parallelize the inner loops. Yes. Typical access patterns are stencils, right? Basically where you need data from all the surroundings or some of the surroundings elements of a data item. And as long as you are in the processor, right, you're reasonably fine. But when you approach the area here, when you are on the boundary between processors, then you need to do communication, right? So if your I is sitting here, then AI plus 1 resides on processor 1, and you need to take the data over, yeah, to get this. And this is a very common thing, and what you typically do is you increase the local data set that you have by so-called ghost cells or an overlap area. So you increase your block size artificially and make sure that the data that you need is then already copied. So you copy the data already up front to make this available. What you also need to take care is the access patterns. When you do like a matrix multiplication here, right, then you should align the rows of A and the columns of B to get less communication, right? Because on A you would iterate that way, and on B you would iterate that way, right? So you have the data local. If you would do it the opposite way, you would communicate all the time. So that's the kind of thing you need to think about. But of course, this is just the very simple example. Typically, it looks like that, where you have a very, very unstructured setup. This is a CFD example, where you have a wing, and of course, as you get closer to the interesting part, which is the top and the tip of the wing, you're having a much, much finer grid. So this is where the problems really come. Good. Questions so far? Okay, then let's get back to the fundamental memory organization that we had, right? Shared memory and distributed memory. The good thing about shared memory is that we have global address space, so we don't need to worry about data distribution. In principle, effectively we do. But we need to synchronize things, right? And there is two main programming models, Threads and OpenMP. Somebody used to program in Threads already? Pthreads, Intel Threads. Okay. OpenMP? Okay. when you are in distributed memory, then you have the issue that you don't have the global address space, so you need to have some mechanisms to deal with non-local access, as we discussed before, right? When you are on this boundary of your data, you need data that is hosted at some other processor. You need some mechanism to get the data across. The main program models here is MPI, Message Passing Interface, and parallel languages. Talk a little bit about. But let's start with shared memory. So something that is being used for quite a long time is threads. The thread is basically an independent stream of instructions that can be scheduled by the operating system. People used to use threads already on single CPUs because it helped actually exploiting, when there was no CPU activity because you were doing I/O or something else, some other activity could be done, right? Nowadays, you can schedule threads on individual cores so they can really execute in parallel, yeah? So basically, you have your main program contains a number of procedures that can potentially be scheduled independently. So in the most fundamental way, thread programming is task parallel programming. You identify a function that you execute in parallel with everything what's going on. And there is an independent flow of control in this thread because you have your own stack pointers, you have your own registers, you have your own signals, and you have thread-specific data. So basically what it looks like is this is a typical process, right? You have a stack, you have the program data, you have a program counter, you have your data. So in a stack, you have, in a threaded model, you have independent stacks, right? And you have independent program counters. But the data is still shared, yeah? So both threads can access array A, array B, right? But they can have also their thread local variables here. So you could, of course, use processes instead. But if you use processes instead, then you have actually, you duplicate everything, including, for instance, also the program text, right? And you could not, different processes cannot access the data that sit in different processes. So you would have to have some mechanism like data copying to access the data. So that's why threads is what is called very lightweight, right? So what you do is you execute into discrete independent tasks. So that's why task parallelism is something very common. Of course, you can also exploit data parallelism. How would you exploit data parallelism in threads? Well, you distribute your loop, right, in n chunks, and each chunk is an independent thread. Yeah? And then, over time, you execute and you can exploit parallelism. Typical models you do is a master-worker scheme, right, where you have one master that assigns work to different workers, a pipelined or peer computing. So what you need to take care of is that each thread has private data, which is fine, this you can compute on, but as soon as you access shared data, then you need to synchronize. You need to protect access to shared data in order to avoid data corruption or access to non-correct data, right? And it's the responsibility of the programmer to do that. Nobody helps you with that, okay? So one pitfall here is you can write a wonderful threaded program, and you really took care that you protected all memory accesses and it's all fine, but your program still crashes. And one of the reasons very often is that you were using some library inside that was not what is called thread safe. So you can be all fine, right? But then your different threads call a library that basically use global memory in an unprotected way. So when you have a multi-threaded program and you use a library, always check that the library says it's thread safe. That's what you typically have on a library. It says this call is thread safe, or this call is not thread safe. What would you do if a call is not thread safe? Can you not use it in a multi-threaded program? Or could you use it? You put a mutex, right? You just make sure that only one instance of this call is active at any given point in time, yeah? By, for instance, putting a mutex around it, correct? But of course, and that goes back to high-performance computing and parallel computing. The more mutexes, the more synchronization we put, the less parallelism we have, right? So that's the trade-off. You need to have a safe execution, but at the same point in time, you want to make sure that you don't excessively synchronize. So one very common thread API is Pthreads, but there is the Intel thread building blocks and so forth. And basically they give you mechanisms to create threads and to synchronize threads, right? So basically you create threads. At any given point in time, a thread can spawn different threads, and then you can, at the end, you exit the thread again and you join your master thread, right? So it's a very dynamic system where you can grow and shrink your tasks very easily. And you have mutexes, condition variables, logs, and barriers. So this is all very fine, but it's really hard to program and hard to program efficiently. I guess those few who have experiences with thread programming says it's low level, right? It's not really the kind of nice C++ style that we are used. So people started to think whether they could do actually some higher level abstraction, yeah, on top of threading. And this is where OpenMP came about. OpenMP stands for Open Multiprocessing, and it's intended to provide a portable, scalable model for shared memory applications. And actually, there's a huge consortium behind that, software vendors, hardware vendors, and so forth. And it started back in 1997. When they started actually, most of these things started with Fortran. I don't know, is somebody here still programming Fortran? Yeah, well, yes, you don't count. This is the wrong community. I should go to some more engineering CFD folks or material folks, then it's 100%. But yeah, that's why things still started a lot with Fortran, but of course there's also C and C++ support. So basically what OpenMP is, it gives you compiler directives. So it's not a parallel language, which is quite important. It's only directives to the compiler, which is a nice feature because you can take your sequential program, you can add compiler directives. If you compile it with a normal C compiler, those directives will be ignored. They are like comments. So you could still check the sequential correctness of your program and then gradually introduce parallelism with it. And the main way is that you have a fork joint model, right? You have a master thread that then forks off into a parallel region where you have a lot of different threads. Then you join, you go back into a master thread and so forth, yeah? So it's also very nice that you can iteratively add parallelism to your program. Yeah? There's lots of features, nested parallelism, dynamic parallelism. The memory model is quite special. You flush, you have relaxed consistency. It doesn't say anything about I/O. Right? And when it comes to the memory model, I mean, the biggest problem when programming OpenMP is that you have your global address space, but as we learned yesterday, effectively, your global address space does not mean that you have the same access time to all data. There is affinity of data to certain processors. And you need to make sure when you program OpenMP that you take this into account. But in principle, it's very, very simple. You do, so this, you basically, well, you include your header file, of course, right? And then in the beginning of a parallel section, you basically say, this is the pragma you have. You say, do this section in parallel, right? With private variables 1 and 2 and shared variable 3, and then you execute this region in parallel, and then you resume. You can do the same with a loop. You say, okay, execute this loop in parallel. So it's a very, very easy way to program parallel computing. Okay, but that only works on shared memory, and we've learned yesterday that shared memory is useful but very limited. So where the real parallelism comes is distributed memory. And here we have the problem that we do need to communicate data between different memory locations. So actually, I can use a distributed memory programming model, to execute on a shared memory computer. It's no problem, right? But not the other way around, for obvious reasons. Okay, who knows what MPI is? You should have gone to the poster yesterday. There was a poster on MPI. The key idea of MPIs, of any message passing, is when you are in distributed memory, right? Then say this process needs data that sits here. Then you use a message passing library so they can say, okay, move data from here over the network to here. Yeah? That's the most fundamental feature. As we said before, there is no need to have one process per CPU or per whatever. It's independent. You can map as many processes as you want on your resources. Typically, you will want not to map more processes than you have cores, right? But you could if you want, but then, of course, you will have inefficiencies. So MPI basically was started to have a standard API. So MPI, when we talk about MPI, we talk about an API. It's only a specification. There is different implementations of this MPI. There is MPI CH, MPIC, OpenMPI, vendor-specific MPIs. Cray has their own MPI, for instance, and so forth. Yeah? So it's really a library where you insert library calls into your program. And it started back in 1992, and 1994, the first version of MPI was published. And then you see what happened here. It took from 97 to 2012 for MPI to go from version 2 to version 3. And the reason was they fell into the same trap that all or many standardization committees have. They had MPI 1 and then 1.1 with a few minor modifications and errors remedied. And I say, okay, this is working fine, yeah? But of course, there is so much more that we could be doing. And they crammed all that, what we could be doing, into version 2, with the result that nobody implemented that because it was very complicated to implement. And that led to the result that actually nobody was using those features, because even if they were implemented, they were not efficient. So people actually stuck with the features of MPI 1. And it took a long time to get rid of that, and with MPI 3 now actually new nice features have come about. And it's still an ongoing process, so we expect MPI 4 to be released relatively soon. MPI parallelization is a single program multiple data programming model, right? So you specify that your program consists of n processes and they all load the same source code, right? So you then, as a programmer, you need to say how you exploit parallelism, because otherwise all would be just executing the same program. So you have you know inside your process, you know which process number you are, and that's, for instance, how you could distribute loop iterations, right? So if you have a loop that goes from 1 to 100, right? Then you would say that processor 0 would do 1 to 10, processor 1 would do 21, and so forth, right? So what you would say here is that your loop boundaries is p times 10 plus 1, then, right? So you can instrument it with the number, your process number, right? You instrument your code. There is no synchronization, no nothing. You have then the library for doing communication. So it's really, each process is a sequential program, right? What you do then to communicate is basically the typical functions you have is what is called send receive. One process says, I want to send data. The other process says, I want to receive data. Yeah? And then data is flowing over the network, potentially involving some systems buffers. So in the most fundamental way, there is always a handshake. One party says, I send, the other party says, I receive, right? And that, of course, then leads to implicit synchronization, because they're not making progress while this is happening. There is, yes, the system buffer is something when you program MPI, you will notice this. This is a nasty feature because there is different semantics associated with the systems buffer. And it can happen that, depending on the semantics, that if you send small amounts of data, everything works fine because data is being buffered and you can have some asynchronicity between send and receive. But when you increase your amount of data, suddenly your program gets stuck. You run into a deadlock. The reason is that for whatever reason, there needs to be, the system buffer is not big enough, so there needs to be direct communication and needs to be a handshake that would never come. That's the kind of nasty thing that can happen in MPI and that you will run into if you do that. Okay. What MPI then basically gives you is a lot of functions. Send receive is the most fundamental one, and then you have a lot of other stuff on top of that, like collective operations, where all processes contribute, like you want to broadcast some data, you want to collect data from all processes and so forth. You can group your processes, you can put topologies and so forth. So it's a lot, it's very rich functionality. In reality, you need 5 commands to do an MPI program. But this is not an MPI course, so we'll stop here. And I invite you to go to an MPI programming course if you really want to do MPI programming. But MPI itself is pretty much like threading. It's very, very low level. So you have to deal with all levels of detail. So it would actually be nice to have some parallel languages that can help you with those things. The problem is that parallel languages so far never really worked as, a compiler has to be very conservative dealing with dependencies. So if you, for instance, if you have a C code and you have a pointer to some data location. The compiler doesn't know if this data location is being used by somebody else and would protect this data access. You as a programmer, you know, no, there is nobody else going at this data location at this point in time. It can't happen, so you are fine. But the compiler would need to protect that, and that makes it very complicated. However, there have been a few explicit parallel constructs being added to some languages, starting with Fortran 90, where parallel loops and array operations have been added. And in the latest iteration of C++, the same thing is happening now. So explicit parallel constructs are being added to the C++ standard. You can have compiler directives like we've seen in OpenMP. But you can also have fully parallel languages, and this is a concept that started probably some 20 years ago, but only gained importance the past couple of years. The idea is what is called Partition Global Address Space, PGAS. Somebody heard that already? So the idea of PGAS is that it tries to provide you still with a single address space over physical distributed memory, right? So you have your global address space, which makes programming much, much easier, but you still need to be aware where the data is located. In order to make this happen efficiently, you need actually a runtime system that provides what is called one-sided communication. So there needs to be a mechanism that over the network I can tap into memory locations of a remote processor without that processor being involved. And this was not there. With advances in memory technology, particularly with InfiniBand, but also Cray networks and so forth, we now have support for remote direct memory access. And hence we can implement those things. There's a couple of languages like co-array Fortran, where you basically have normal Fortran, but you have a co-array, and the co-array is basically telling you where data is located, right? So you say this is located on a certain processor, right? And you can have different intervals and so forth. So you have your global address space, right? You don't need to worry about the variables and all that, but you need to say where the data is, and then the runtime system will make sure it fetches the data. There are similar things around C, which is called Unified Parallel C, which basically has a global pointer that goes over the memory space. And something that came very recently is called GASPI. That's actually now an attempt to standardize a low-level PGAS-like interface. It's a library, which makes it more easier to implement. It is supporting, well, all networks that are around. It's supporting accelerators and so forth. And the key feature is that it has this asynchronous one-sided communication. It's thread safe, right? Every thread can communicate. And there is, for instance, an implementation of this around from the Fraunhofer Institute, which is called GPI, that you might use, and has been tested scaling really, really well. So this is an imaging application which scaled up to 65,000 cores, right? Almost perfectly. And they do the same thing, right? So they deal with data transfer, they deal with synchronization. As we said yesterday, communication architecture, we need mechanism for data transfer and synchronization. And the key concept is a one-sided communication. So by doing this, data transfer and synchronization are decoupled. In MPI, data transfer and synchronization is the same thing, right? You send, receive, you wait for a handshake, and that's how you synchronize. Here you can basically say you can't access data without the participation of the remote site. You can get data from some other process, and you can put data into some other process. And the initiator specifies all the parameters, the source location, the target location, and the message size. It's actually a feature that is now, since MPI 3, also available in MPI, but not as efficient as in implementations like this one. You cannot just access all memory, but you need to say, and here they call it segments, to say, this is the memory area that I make available. This is my global memory area. This is my private memory area. Nobody touches my memory area here. That's how you avoid that problem. Yeah, of course, if you would open all my memory, then yeah, somebody could come and destroy everything. Yeah? So you need to say, okay, this is the area where I allow communication. Yeah? And then basically, yes, you can, you say which subsets of the data will be transferred, and you can basically say you do a write, yeah? But then, of course, if you do a write, this guy is not involved in the write, so it does not know when the data is available. Yeah? So you would actually then have to notify the guy, say, hey, I sent you some data. Yeah? Now this guy wakes up and can use the data. The same way, this node does not know when the write is actually finished, right? Because you say, I write, so I ship my stuff. I have no idea how long it takes for it to get over, so it will need to wait for a notify before actually going to reuse the data. So you see there is now a difference between the data transfer itself, the communication, which is blue, and the synchronization, which is red, right? So you decouple those concepts, and that allows you a much more efficient implementation. This is a very flexible system. It allows for shrinking and growing node sets. It can have time-based blocking. It has groups. It has collective communications and so forth. It also supports fault tolerance. You have timeouts, checkpoints, and so forth. And in total, it's a relatively rich standard, but same as with MPI, you only need to have a few fundamental functions. So basically, we have now a couple of different ways on how we can program, right? We have threads, we have OpenMP, we have MPI, we have PIGAs, parallel languages. If you program a large-scale system in practice, what would you use? Most people use almost all of them, yes. So what you would do probably is you start with a pure MPI program, right? But then you would need to actually be more efficient on shared memory. You would say instead of having multiple MPI processes on your shared memory node, you would have only one MPI process and use some shared memory concepts underneath. You would probably start with OpenMP, but there might then be functions where you need to resort to threading because OpenMP is not efficient enough. And then you might actually include some PIGAS concepts as well for certain parts of your program where you really need to decouple. So that's the bad news, right? There is no one programming model that you can use. People tried hard, but no. So you probably use, well, if not all of them, you use at least two of them, 2 or 3 of them. And now we make things, of course, even worse, because now we've only looked at normal processors, right? But we learned yesterday that we have actually additional hardware that sits on nodes, right? What was that? We have our Intel processors on the node. We might get this Spinnaker, but let's forget about that, because that you can't program it anyway. What else can we have? What are you using for your deep learning, your deep neural networks? GPU, right. Do you program your GPU with MPI? No, right, yes. So to make things even more complicated, we need yet another programming model to go to GPUs, right? And basically, what the most common way to program GPUs today is CUDA. The drawback of CUDA is that it's a proprietary solution that's only available through NVIDIA. That's essentially their way to keep their market power. Yeah? We have lots of CUDA programs that only run on NVIDIA resources. That's a language extension that allows you to define and launch so-called kernels. The kernel is the data parallel function that should be executed on a GPU, right? So again, it's kind of you have a task parallel model, you launch a task in parallel on your GPU. The task itself is highly data parallel, right? As we learned yesterday, you need to explicitly move data back and forth between your CPU and your GPU. They have different memories. And then, of course, you need some mechanisms to synchronize, right? So you have a lot of cores on your GPU, and you group your cores into what is called a streaming multiprocessor. It's a SM, and they have a shared memory, right? And then you have a grid of thread blocks that you map into these streaming multiprocessors. So you have multiple threads within a block that would then map to the individual cores of a streaming multiprocessor. You don't need to know really about the hardware details, right? The runtime system will take care of. You just try to have as much parallelism as possible, right? You overscribe the system, and then the system will schedule the threads on the system. So we talked a lot about loop parallelism, right? This is what we typically do, and as that if we do MPI, for instance, then we would split this 0 to 10 in something like we did over here. In CUDA, we don't have loops, right? We just have a single instruction, right? But this is being executed by all the threads we have, right? So you need to instrument it with your thread ID. Yeah? That's an internal variable that is unique to every thread. Like for an MPI, you have your process ID, and then the runtime system will basically schedule these. Yeah? You need to add a global specifier so that you know that this is a GPU kernel. From your main program, you need to launch this kernel, right? So you say, this is something that I want to execute on a GPU, and you say how many blocks you want to have per grid and how many threads you want to have per block, and then it's being executed. You have ways to allocate memory, of course. You have a classical malloc and free, and you need to move data to the GPU and from the GPU by memcopy, right? And that's the most expensive thing, right? If you need to move the data back and forth. And then you have synchronization mechanisms, right? And yes, finally, you exited the kernel. So this is all also, again, very, very low level. So that's why people are building higher level abstractions. Particularly, you might have used some of the DNN libraries like Caffe, Torch, and so forth, right? So people try actually to give you higher level tools already that are using CUDA underneath. There's also linear algebra solvers like BLAS and so forth. So a lot of different things there. And there's also an attempt to have higher level abstractions. One is called OpenACC. That's very similar to OpenMP. And actually the way is that OpenACC eventually will be incorporated into OpenMP. So at least there people try to get rid of yet another programming model. But still, even if, say, OpenMP will be efficient or will be good for programming GPUs, there will still be occasions where you need to go to CUDA. So now we've learned 5 different ways to program an HPC system. And when you do this, you still need to think about vectorization to exploit the vector unit. You need to think about your caches, your data access patterns, and you need to think out a little bit about instruction level parallelism and so forth. So yes, unfortunately, programming systems in an efficient way is very hard. You can get very, very quickly to a parallel program, like with OpenMP, but even MPI, you can be very, very quick in having a parallel program. Having this parallel program run efficiently, that's very hard, unfortunately. So, questions, comments, concerns, how to program parallel systems? I guess the main advice is, if you can use the higher level tools that are being provided. But I think, excuse me, even if you use them, it's good to have a basic comprehension and basic understanding what's going on underneath. It will help you understand a lot what is happening and why you see certain performance patterns.